Hi everyone, this is a video of me going through the Unit 8 progress checks. There was A and B for the multiple choice. A bunch of you had questions on certain problems in each, so I'm just going to do the questions from progress check A in this video, and I'll make another video of me going through question B. I have my calculator here. I'll be doing the problems as I go on that. I'm going to make this video skippable, so you can just skip to the parts you need. The video is obviously going to be more than 15 minutes, I think, because you're going to be watching me type things in my calculator. So you don't need to watch every minute of it. Just, if you want to watch all of it, that's obviously fine. But you can skip to the parts that gave you the most trouble. And it's very important to be going through these problems because typically people do better on the free response part of the exam than the multiple choice. So the more multiple choice practice you get, the better. So for number one, as soon as I see average value here, what's the average value of f? I'm going to think of this formula. And remember, whatever you want the average value of, that's what your integrand is going to be. So if I want the average value of this function right here from 2 to 6, I'm going to do 1 over 6 minus 2, so 1/4 from 2 to 6. And if this was a free response, you could just write f of x there because the problem is calling this thing f of x, but I'm just going to write it there so you can see exactly what I'm doing. So then I'm going to be going to math 9 and typing this thing in. So I'm going to be going from 2 to 6, and I'm going to insert, okay, I don't feel like inserting a fraction. 1/4 is 0.25. Okay, and I'm going to be putting in x squared plus x and cosine of 5x dx. All right, and that is how they are getting the answer of B here. Number two. So number two is a problem that we haven't really, we don't really see this problem too much. It's saying, what's the net change in velocity? What we do answer a lot is, what is the change in position? And in fact, there is a name for that. You know that change in position is displacement, and I'm going to abbreviate displacement. And displacement, as you know, is the integral from A to B of velocity. It's not the absolute value of velocity, because absolute value of velocity, if you did that integral, it would be total distance traveled. So just straight up velocity, the integral of that, it would give you change in position. And just to confirm that this would be position, what are the units of velocity? Well, it's meters per second. What are the units of dt? That's seconds. You're left with something in meters. So it is s of t position, but more specifically, it's the change in position. Okay, so let's go up a derivative here. Instead of change in position, if I want the change in velocity, what I'm going to do is, instead of the integral of velocity, I'm going to do the integral of acceleration. No absolute value here. And let's check the units here. That would be meters per second squared times dt is seconds. Meters per second squared times seconds is meters per second. So you know your answer is going to be some kind of velocity. It will be the net change in velocity. Okay, so if I want from 0.75 to 2.25, that is how they are getting this set up right here. All right, and so they're just putting the velocity function right here. And if you type that into your calculator, you should get the 0.984. I'm going to plug my laptop in. Give me one sec. All right, number 3. What is the area of the region in the first quadrant bounded on the left? Oh, okay. You know what I noticed about this problem set? There was a lot of questions about left and right. So whenever I had that after school session and included some problems like that, it's because I noticed AP's been trending towards more left and right, not just top minus bottom. Okay, so the thing that's interesting about this problem is you don't even have the graph. And like, if I look at this, I don't necessarily know what x equals y squared of y to the fourth plus 1 looks like. I mean, who knows what that looks like off the top of their head, right? And then x equals 2y. I could think, all right, if I solve for y, it'd be 1/2 x. Like, that is a line with a slope of 1/2. This, I mean, I don't really know what that is, but the thing is, you don't have to know what that is. I mean, it's some kind of square root, so I'm going to take a wild guess and say it looks like this, okay? And then I have this line, x equals 2y. So there's some kind of area here, And I'm going to label this here so I remember. This is y square root of y to the fourth plus 1. And then this is x. I'll put x equals here. This is x equals 2y. All right, and it's actually really nice that they gave us equations that are solved for x, because think about this. In order to find this area, I'm not doing top minus bottom. I mean, you could, because the top curve and the bottom curve are probably always the same, but I know that the right curve is always x equals 2y, and the left curve is always the square root. So I'm actually going to do right minus left like this, because the right curve is always this, the left curve is always that. So whenever I set up my integral here, without even knowing exactly what it looks like, I know I'm going to do right minus left. And this whole thing is dy. Everything has to be y. The only thing we have to figure out is, where do these two things intersect? And remember, to find right and left, to find the distance of a horizontal line segment, you subtract x values. These are already solved for x, so I'm solving what x equals. Okay, so I think the hardest part of this problem, once you figure out what this looks like, is figuring out the intersection points. So here we go. I need to find out where 2y and y squared of y to the fourth intersect. And I can't put y in my calculator and expect to get anything. So I'm going to graph 2x, knowing that whatever x value I get is actually a y value. So that, I think, is what makes these problems a little bit more challenging. Okay, so I have x to the fourth plus 1 times x, and then I have 2x. And let's just zoom standard this thing, because I don't really know what kind of window I should be expecting. All right, and it says in the first quadrant. So now that I know, I'm going to zoom in. And if you're doing this on your calculator, it's a good idea to do this as well as I'm doing it. All right, so let's find these intersection points. Intersect, whoop. And let me put my cursor. Come on. Okay, that should work. All right, 1.316. So you know what I'm going to do? I'm going to store this as B, because it's the further one to the right. So I'm going to go home. I'm going to store this. Why didn't I do that? There we go. Store it as B. Okay, and then I'm going to do the other one, second calc intersect. And I'm going to have to do the one further to the left. I'll call this one A, because it's like the first one, the smaller one. First curve, second curve, guess. Oh, 0. That's nice. I don't really have to store that. So I know that I'm going from 0 to whatever I called B. It was like 1 point something. And let's try this. See if we get the right answer. Oh, crap. Oh, I guess this works. Okay, math 9. I never knew how to split the screen like that. Okay, from 0 to B of, here we go, 2x. And again, I'm putting x in, knowing that it's y. Square root of x to the fourth plus 1 dx. Yay, we got it, 0.537. All right, cool. So, the split screen is cool, but I kind of don't like it. So that was that. That's how we get A here. Next one, 4. The regions bounded by these graphs are shaded in the figure above. What is the sum of the areas of the shaded region? Okay, so I'm going to find this area, and then I'm going to find this area, and I'm going to add them up. So I guess I need all these intersection points here. And I know that because, all right, in the first part, this is the upper curve. And when I say this, that has to be the line. So x over 2 is on top, and then the sine wave, sine squared of x, is on the bottom. But then for the second part, look which one is on top. That's sine squared of x. And it's helpful to label it just to really emphasize this. X over 2. And I'm going to do top minus bottom. And to find the length of a vertical segment, I should be subtracting y values, which is why it's so great that they gave us these solved for y. They are in terms of x. They are solved for y. Okay, so I'm going to do an integral of top minus bottom. That's the first part. Don't forget your dx. Then I'm going to add on the next one, which has sine squared on top minus bottom, and I'm going to find where they intersect. I feel like this is probably 0, but I'm not going to assume that because sometimes it looks like it's 0 and it's not really 0. So you should never assume. Okay, I'm going to type this in as quickly as I can. X over 2. And remember, sine squared of x is sine of x squared. And I'm in the first quadrant. One too many parentheses. I think I'm good now. Okay. Whoa. So let's trim this thing at like 3. I don't think I need to see more than that. And oh yeah, I only need to go up to like 2 here for my y's. There we go. Okay, that's better. So now I can see my 2 pieces here. So I'm going to do intersect and let's see what we get. Okay, I'm pretty sure this is going to say 0. Let's find out for sure. Let me get this cursor over there. And enter, enter, enter. Yep, 0. Okay, let's find the next one. So I'm going to call that one 0. I'm not going to give it a label of A or anything. This first decimal intersection point, I'm going to call A. Okay, so I have to go home. And I'm going to do, I don't know why it does that, store. I have to hit clear first for some reason. Store, that thing is A. So 0.555. Now I'm going to go back to graph. Second trace, I'm hitting 5 for intersect. And let me get this blinky blink close. And there we go. Second trace intersect. Woo. And enter, enter, enter. 1.849. Okay, I'm going home. I have to hit clear first for whatever reason. Store it as B. Cool. So I'm going to go from 0 to A. A was like 0.55 something. And then from A to B, B was like 1.89 or something. So 0, A, B. Those are the X values. All right, now I have some typing to do. So I'm going to do math 9. And let me actually pause this thing real quick. Here's what it looked like when I typed it in. Oops, that's not what I want. Oop, that's not what I want. Okay, there we go. So I typed this in, what I had in blue right there, x over 2 minus sine squared, and then sine squared minus x over 2. I got the answer at 0.249. As a reminder, alpha y equals made my fraction of x over 2, in case you forgot that. All right, cool. Number 5. So the base of a solid in the region, or is the region in the first quadrant bounded by the x and y axis and this graph. Again, they're giving us a graph where we don't really know what it looks like. It has a vertical asymptote at -1, but because we're in the first quadrant, that doesn't matter. It has an x-intercept of 2. I know that. The y-intercept, if I put 0 in for x, it'd be -2 squared, which is 4 over 2 times 0 plus 1, which is 1, so 2. So y-intercept is also 2. All right, it probably looks, I don't even know, something like this, okay? This is a complete guess. For each solid, or for the, oh my God, why can't I read? For the solid, each cross-section perpendicular to the x-axis. Okay, so here's my x-axis. Perpendicular to that looks like this. And it's going to be a rectangle whose height, this question comes up all the time, a rectangle whose height is 3 times the base. They're calling the base the width, and they're saying, hey, the width is in the xy plane. So this is your width, and then the height, imagine this is 3D. It's coming up out of your screen, hitting you in the face. This is 3D coming up out of the screen. So I have all these rectangles, and of course, like the smaller your width is here, the smaller your height's going to be, but you have a bunch of rectangles like that. And so my rectangle area, I need that. First of all, I need to know, like, what is the width? What's an expression for the width? Well, in order to find the distance of a vertical line segment, or like the length of it, it's top minus bottom. Top is my function, x minus 2 squared over 2 times x plus 1, minus bottom is 0. So it's really just the function that they give me. Okay, so that is what the width is. And then in order to find the area of a rectangle is base times height. They're calling the base the width. And then the height is 3 times the width. So width times 3 times the width, okay? And we actually had a question on a test like this. So I guess I'll write this thing out. I really don't want to, but it's okay. So I'm going to do this times 3 times that. So you know what I'm going to do? A more efficient way of writing this is put a 3 out front and then square this. So whenever you do your integral, oh, I need to know the volume of it. So I actually needed to know where this thing hit the x-axis. So it's good that I found the x-intercept because like my rectangles start here and chop, 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 chop. They end here. So remember, in order to find an x-intercept, you let y be 0. That means your denominator will 0 out. So I set x minus 2 squared equal to 0, square root each side, and x is 2. Okay, so I'm going to have an integral from 0 to 2. This is all of, like, in terms of x, okay? So I'm going to have 3 times base times height here, squared. The 3 is not squared, dx. All right, let's type this in and see what we get. I could bring the 3 on the outside. Doesn't matter. You can keep the 3 on the inside. I'm going to go from 0 to 2. I'm definitely going to do a fraction here, alpha y equals, to make this thing a little more manageable to type in. So I have x minus 2 squared, and then I have 2 times x plus 1. All right, here we go. Oh, I didn't square the whole thing, did I? Shoot. Wait for it. I'm going to close those parentheses and square. Okay, I think I'm good. Yes. Okay, good. We got it. All right, question number 6. Here we go. The graph of this continuous function is these line segments. They're not telling us the equations. I mean, we could easily get these as equations. What is the average value of f on this interval? Okay, as soon as I hear average value, I am thinking 1 over b minus a. So 1 over 6 minus negative 1, which is 1/7, from a to b, negative 1 to 6 of my function. Okay, so remember, there are 2 ways to do an integral. In order to do this integral, I could do an antiderivative, but it's like, well, what am I doing the antiderivative of? You could find these 3 equations and do the antiderivative of each and then plug in the endpoints. But that's kind of a lot of work because remember, the other way to get an integral is just the area under the curve. So this integral right here is just this area. And I think that's way easier because this area, I can find that real quick with geometry. So I'm going to continue here. This is 1/7 times, just let's do this area. I'm going to do this triangle first. That's 1/2 base times height. So 1/2, 1 times 2, plus, now let's do this area here in the middle. This is just a rectangle. So I have 1, 2, 3, 4 times 2, plus, now let's do this one. Oh, trapezoid. Okay, so that's going to be 1/2 base 1, 2, plus 1, 2, 3, 4 times height 2. And I mean, I could obviously break this up into another triangle and a square, which would probably honestly be easier, but I've kind of already committed to this. So 1/7 times 1/2 times 1 times 2 is 1, plus 8, plus, these will cancel, this is 6. All right, that's 9 plus 6 is 15 times 1/7 is 15 over 7. Yay. Okay, question number 7. If, ooh, I love this one. As I was copying and pasting this Jamboard, I read this and I was like, this is a good problem. If the function f on this interval is, if the average value of the function on this interval is 8, what is the value of this? Because I actually haven't seen College Board ask one like this, and it's kind of an interesting way of asking a student to use the properties of definite integrals. So I'm going to start with this statement right here. And I'm going to break it up into 2 separate integrals. And I'm also going to take the 3 out of the f of x integral. Okay. And, I'm going to keep the 2 with the x here because it's not that complicated. All right. So here's the deal. Like, how do I know what this is? Because I don't even know what f of x is. Like they don't give me a function. I can very easily find this just by doing an antiderivative and subtracting the endpoints. So I'm going to get to that in a minute. But let's see, what can I figure out from this information here? I know that the average value of f, so 1 over 4 minus 1 from 1 to 4 of f of x. I know that this average value is 8. Okay, so what does this tell me? This tells me that the integral from 1 to 4 of f of x dx equals, wait, so this is 1/3, right? 1 over 4 minus 1 is 3. So what if I multiplied each side by 3 here and canceled and multiplied by 3 here? Then I would just have this integral equaling 8 times 3, which is 24. And oh my gosh, look at this. The integral from 1 to 4 to f is 24. So I can go back here and do a clean substitution and put 24 in for this. 72, right? Yeah. Okay, let's go back to here. I'm going to do a quick antiderivative. The antiderivative of 2x is x squared from 1 to 4. So now I have 72 plus 4 squared minus 1 squared. This is FTC part 1, fundamental theorem of calculus, plus 16 minus 1. So that would be 88 minus 1, which is, in fact, choice D, 87. Number 8, a particle moves along the x-axis with this velocity. If the particle's position is 3 at time t equals 0, which of the following gives the position of the particle at time equals 2? Okay, so I'm talking about position here. I know a position initially. I want to know a final position. And I know information about the derivative, which is velocity. This sounds like the fundamental theorem of calculus part 1, which some of you, based on your last test, need a review on, FTC part 1. The integral from a to b of f prime of x dx is the antiderivative at the endpoints. That's it. And you can rewrite this to look a little bit more like accumulation by adding f of a to each side. So then I have f of a, my function at my initial, plus the integral of the rate. Remember, the integral of a rate gives you a net change. That was from like the corn problem. That's when we first started talking about it, children of the corn, equals the function's final value at b. All right, let's personalize this here. This would say, well, what's my starting time, I guess? Time equals 0. Plus the integral, my time starts at 0 and ends at time 2. Instead of f, instead of f prime, I need to put velocity, t minus 1 e to the 1 minus t dt. That will equal my function at b, which is 2. Okay, what is f of 0? F of 0 is 3, so I'm going to put 3 here. So 3 plus the integral from 0 to 2. Yep, bingo, we got it. Ooh, this one. All right, so Rachel asked me about this one when she was working on this after school, and it was a tricky problem, and I kind of was debating between choices B and C. I remember we both agreed, like, it can't be A, it can't be B. Those are too large or too small. And I was reading this really carefully to see how they got this, but let's just review a couple things here quick. First of all, what is this graph? This is a graph of velocity. So whenever the velocity is positive, my particle is moving right. When my velocity is negative, my particle is moving left. And then when my velocity is positive, I'm moving right again. So what's happening here? I don't know my starting position. I know that, like, look how little this area is. I move a little bit to the right. Then I move kind of a lot to the left for the next 1, 2, 3, 4 seconds. I move left. Woo! And then for the next 1, 2, 3 seconds, I move right. And I know I end up further to the right than when I started because they tell us a particle's displacement is 100 units to the right. So that means this distance right here is 100. I'm 100 meters further to the right than where I started, or units, I guess. The total distance traveled is 1875. So, okay, let's review something here. If I consider the area, the signed area, including positives and negatives, that would be this. from 0 to 8. The integral of velocity gives you displacement. If I consider everything being 1, 2, 3, 4, 5, 6, 7, 8, if I consider everything being positive, that's still there. And then that would be like this. It's reflected above. And then this one stays as it is. This is a rough sketch. But now all my movement is positive. So in order to go from here to here, I did the absolute value of the graph. So visually, it's the absolute value of velocity. And that gives you total distance traveled, which is 1875. And displacement was 100. So what am I even looking for here? I'm looking for what's the total distance that the particle travels while moving to the left. So I only move to the left one time from 1 to 5 seconds. So I basically want to know how much is this? Like how far am I moving right there? Mama. All right, sorry about that. So anyway, I want to know what this shaded area is basically, the area under the x-axis, or you can call it this. So I'm going to do it the way that College Board suggested, and that is with a system of equations to solve for the unknowns. Because I have two unknowns here. The two unknowns are how far I moved to the right and how far I moved to the left. So I'm going to call how far I moved to the right A, and how far I moved to the left B. And here it's A and B. So in order to get displacement, let's see here. In order to get displacement, I take A and I subtract B because I want signed area for displacement. I want to consider like the movement left and right. And I already know displacement is 100. And then for total distance traveled, I want to add these up. I want the absolute value, which means that A and B are positive. So I'm adding A and B together, and that gives me 1875. So now I'm going to treat this as a little system like this. And you know what I'm going to do? I'm going to subtract these. No, actually, I'm going to add them to show you something. A plus A is 2A. Negative B plus B cancels out, and this would be 1975. So 1975, what I need to do is, go away, divide by 2 on each side. So 1975, I'm going to use a calculator here. You could probably get that in my head, but 987.5. Mommy. So that would give me an A value of, what was that again? 987.5. 987.5. All right, but that tells me how far I moved to the right. So the combination of these two together is 987.5 units to the right. I want to know how far I moved left, so I really want to know what B is. So I know that A plus B was 1875. So that means 987.5 plus B is 1875. You know, so to get B alone, I'm going to do 1875, and I'm going to subtract 987.5, 887.5, 887.5. Whew! All right, that was number 9. This one here, the velocity of a particle is given by this. Which of the following gives the total distance traveled? Okay, so I have to tell you something about this. There's this video that I made optional, which I now know I should never make optional again. Displacement versus total distance. This video was optional to watch. And, oh no, it wasn't that one. It was a video I didn't even assign. Okay, just kidding. It wasn't that video. But there's another video I didn't assign that I am now going to assign again because I know College Board is asking questions like this. So let me give you a quick recap of how we're going to do this. Okay. What the heck? Oh, man. That's unfortunate. One sec. Sorry about this.
Well, now you're all done.
Not yet. Alrighty. There we go. Okay, in order to get total distance traveled, I know that I need the integral from a to b, which would be from 0 to pi, of absolute value of velocity. If I didn't have absolute value, it would just be displacement. So this is going to be from 0 to pi of negative sine of t minus pi over 4 dt. So the thing is, this is by hand. There's no calculator on this one. And we don't really know how to do integrals of absolute values. So there's a way that you can rewrite this without an absolute value, and it involves breaking it up. So absolute value means this whole thing is positive. So let's see, is this always positive? Is is velocity always positive? So let's see if velocity, first of all, is ever 0. So what I'm really doing is I'm kind of finding critical values because this is a derivative, and I'm going to set this equal to 0. So if I divide by -1, it'll just cancel this negative here. So sine of t minus pi over 4, 0 over -1 is 0. I'm going to do sine inverse of each side because I want to slowly get to t. So t minus pi over 4 is sine inverse of 0. Sine inverse of 0. What angle on the unit circle has a y value of 0? Well, 0 and pi. And then if I solve for t and add pi over 4 to each side, add pi over 4 to 0, that gives you pi over 4. Add pi over 4 to pi, and that's 5 pi over 4, right? But that's outside my interval. So, okay, shoot. At pi over 4, velocity 0. So I stop at pi over 4, which means that is a potential spot where I could change direction. And I need to know when I'm moving to the right and when I'm moving to the left. Okay, so let's do some quick critical values here. A number less than pi over 4 is pi over 6. A number greater than pi over 4 is pi over 2. So we have to do some quick plugging in here. Lots of good trig review here. Plugging pi over 2 into the derivative, into velocity. That's negative sine of pi over 2 minus pi over 4, which is negative sine of, okay, that would be what, pi over 4? Well, sine of pi over 4 is positive, but it's like negative that. So this is a negative value. And then let's do this one. Negative sine of pi over 6 minus pi over 4. That will be negative sine of, okay, this isn't going to be on the unit circle, but let's just subtract it real quick because I'm going to show you something. Darn it, I have to get common denominators. Okay, that's kind of annoying. So what is that? 2 pi over 12 minus 3 pi over 12. The point is it's a negative angle. And even though I don't, like, negative pi over 12 is not a standard angle on the unit circle, but it'll be somewhere down here. So the sign of that will be negative. So this already is negative. Then it's negative that, meaning it's positive. Okay, so what all of that means is from 0 to pi over 4, velocity is positive, so I'm moving to the right. And then from pi over 4 to what, pi? Velocity is negative, so I'm moving left. If I move to the right, my displacement is positive. If I move to the left, my displacement's negative. So to get total distance traveled, what I need to do is I'm going to have to go from 0 to pi over 4 of velocity. And because velocity is positive here, like I'm moving right, I can just do that integral and it'll give me a positive amount. If I then do the integral from pi over 4 to pi of velocity, well, okay, remember from pi over 4 to pi, velocity was negative, so I'm moving left. So this integral would give me a negative amount. But remember, total distance traveled, you want to be like accumulating all the distances moved. So you want to take this integral and you want to subtract this integral, because subtracting a negative value will be the same as like adding. So that is why they're getting choice D here. You definitely don't want choice B because they're doing the opposite from 0 to pi over 4, but velocity is already positive from 0 to pi over 4, so you don't want to subtract that. Okay, next one. The rate at which sand is poured into a bag is modeled by this function R, where R is measured in milliliters per second. T is measured in seconds after you start pouring. How many milliliters of sand accumulate in the bag? Oh, this is a nice one. Accumulation, classic accumulation problem. You do the integral of the rate, which will give you the amount accumulated. This one is much quicker than the last couple that we had. So I'm going to do math 9. Oh, nope, I'm not. Because this is a no calculator problem because I don't see any decimals in my answers here. All right, so this one is quick enough to do an antiderivative of. So I'm going to do 15t squared over 2 minus 2t cubed over 3 from 0 to 2. All right, luckily when I plug 0 in, it's just going to zero out. The 2 hopefully isn't too problematic. I'm going to plug 2 in. What is this? 2 cubed over 3 minus 0. 15 times 2 squared minus 2 times 2 cubed. Okay, so this would be 2 squared is 4. 4 over 2 is 2. So I really have 15 times 2, which is 30, minus, this would be 2 cubed is 8, so 16 over 3. Okay, let's get a common denominator over 3. That'd be 90 over 3 minus 16 over 3, which is 74 over 3. C. 12. A traffic engineer developed this function R to model, okay, so this is a rate that cars pass a certain intersection over the 8-hour time interval where R is measured in, I'm just going to put cars per hour, cars per hour, and T is the number of hours after 6 a.m. So this is 6 a.m. at 0. According to the model, how many vehicles pass through the intersection from 0 to 8? Okay, another accumulation. So I'm going to do an integral of a rate, and that will give me the net change or the amount of vehicles. The rate so is positive because I'm always accumulating vehicles. So, all right, there's 2 ways to do an integral. One is with area, one is with an antiderivative, the FTC part 1. I don't have a function for R, so I'm just going to do an area, okay? And it's not asking me for an average value here, right? It's just saying how many vehicles. So remember, rate is in vehicles per hour, dt is in hours. So when you multiply those, you end up with vehicles. So that is why this integral of a rate gives you the amount of vehicles. So this is just area. So I'm going to break this up from here to here. And okay, base times height. Here we go. 2 times 1800 plus, oh boy. Oh, okay. No, here we go. Here's a trapezoid. So I have 1/2 times base 1, 1800 plus base 2, 2400 times the height here, which is 2, plus, these are some big numbers here, this trapezoid right here. Okay, so 1/2 times base 1, 2400 plus base 2, 1400 times the width or the height, which is 2, plus, a square, thank goodness. This square. Actually, it's not even a square. It looks like a square, but look at this little break in the graph. 1400. Well, I guess we got to add these numbers up. 1800 times 2. Huh? What is it? 1 sec. Are you done? All right, so what I did here is I combined these 4 expressions together. The 1/2 and the 2 canceled for both of them. These 2 numbers added up cleanly to 8,000. When you add these up, you do in fact get the 14,400 that was listed. Okay, next one. Let R be the region in the first quadrant bounded by this graph here and this graph here. So in this one, they do give us a figure as shown above. We want to know the area. Okay, so this one you could technically do top minus bottom, because the top curve is always this curved function. The bottom curve is always this linear function. But the thing is, look at how the problem is given to you. They already list these as x equals. So I'm thinking I kind of want to do right minus left, because to find the length of a horizontal segment, I want to do subtract the x values. So I kind of like how they're already solved for x. So the line one has to be x equals 4y, because like if you were to solve for y, it'd be 1/4 x. And the curved one has to be x equals y cubed. And if you did solve for y, just so you know, it would be the cube root of x. So like you very easily could do top minus bottom, but I'm going to do right minus left, because you know what? This is a no calculator problem, and I think it's going to be easier to evaluate without a cube root and a fraction in it. Okay, so if I'm going to be doing right minus left, I'm subtracting x values. So that means I'm going to do 4y minus y cubed. Because there's y's here, it's going to be dy. And everything is with a y, so from a y to a y. So this starts at y equals 0. This appears to go to 2. Can I confirm that, though? That would be 4y equals y cubed. 4 equals y squared. Square root 2 equals y. Yep, that's right. Okay, so I'm going to now do an antiderivative here. All right, let's do this antiderivative. So I'm going to come over here. So this would be 4y squared over 2, which is 2y squared, minus y to the 4th over 4. That should be a 0. I'm going from 0 to 2. So plugging in 0 is just going to make everything 0 here, so I don't have to worry about that. This will be 2 times 2 squared minus 2 to the 4th over 4. Again, minus 0. So 2 times 2 is 4. 4 times 2 is 8. Minus 2 to the 4th is 16. 16 over 4 is 4. So I end up with just 4. Okay, next one. Let R be the region. Okay. This one's kind of interesting. Let R be the region between the graph of this, the x-axis, and the line x equals 1.5. Oof. Okay. So I'm not sure how many people know what tan inverse of x looks like. Let's remember, like, what does tangent look like? Tangent going from negative pi over 2 to pi over 2. Remember, tangent was just repeats of this same shape over and over again with more and more vertical asymptotes. So the inverse of that is a reflection over the line y equals x. So tangent inverse of x actually looks like this, and it has a horizontal asymptote now at pi over 2. All right, so it's the region between this and the x-axis, and the line x equals 1.5. So here's 1.5. So we're really looking at this right here. All right, so notice all of these are dy. They are in terms of y, which leads me to believe, or I don't just believe it, I know it, I'm going to do right minus left, not top minus bottom, because top minus bottom would be a dx problem. So I have right minus left, which means I should be subtracting an x minus an x. Well, 1.5 is already like equal to x. However, here, this curve is y. Okay, so I just need to solve for x quick. So if I have y equals tangent inverse of x, I need to do tangent of each side, tangent of each side. So tangent of y is equal to x. So x equals tan of y. Okay, so that means I had to do right minus left. The right function is x equals 1.5. The left function is x equals tangent of y. So I know it has to be 1.5 minus tangent. So it can't be that. Well, these are both 1.5 minus tangent. What is the difference here? Yeah, it's this. So how on earth are we going to figure out what that should be? So I should be going from a y value to a y value. I have to know when those two things are equal to each other. So I have x equals 1.5 and x equals tangent of y. So let's set those two equal to each other and see what happens. X equals 1.5 equals x equals tangent of y. Okay, so I need to solve for y because I need to know what y value these intersect at. So I will do tangent inverse of each side, tangent inverse of 1.5. That was kind of tricky. So it's this one that has tangent inverse of 1.5. C. All right, this one here, the region bounded by these graphs. So y equals 2x is this one. So 2x, and then I have this cubic here, 3x squared minus x cubed, and 3x squared minus x cubed. They intersect at 0, 1, and 2, which gives the sum of the areas. Okay, so I'm going to do top minus bottom. So the first one should go from 0 to 1 of the 2x minus the cubic with the dx. And the next one should go from 1 to 2, 1 to 2 of top minus bottom. The cubic, I guess I'll write it out here, minus the line, 2x, dx. And the only one that does that is this one. The other ones just don't have enough going on there. And this one tries to combine everything, but you can't combine them because the top and bottom curve change at 1. So B. Okay, only a few more here. The regions bounded by the graphs. Oh, this is interesting. This is a line. It is mx plus b form. The slope is just written in an interesting way. So this is my line here. So I have negative 2 over pi x plus 1 and negative 2 over pi x plus 1. And then here's cosine of x and here's cosine of x. Which of the following is a sum of, okay, so I want the shaded area. All right, all of these are dx, so it's going to be top minus bottom. I'm going to subtract y values, so everything will have x's in it. All right, so from 0 to pi over 2, so this, like, you definitely can't do it all just from 0 to pi because the top curve at first is cosine, and then the top curve next is the negative 2 over pi x plus 1. So it has to be C or D. Okay, at first the top curve is cosine, so it's going to be cosine minus the line. Then it's going to be the line minus cosine, top minus bottom. All right, so C. 17, the base of a solid is the triangular region in the first quadrant, bounded by the graph of y equals 5. So this is a line with a negative slope starting at 5, and the x and y axes. So this is my base here. So y equals 5 minus 5/3 x. For each solid, or for the solid, each cross-section perpendicular to the x-axis. Okay, so I know that a random base looks like this. I'm perpendicular to the x-axis, and I have a square. Okay, so this is volume by cross-section. So picture a square coming up out of the paper here. And depending on how big the edge is, the square will change shape. All right, so this one's not too bad. A random base length will be top minus bottom, a y minus a y. So 5 minus 5/3 x minus 0. The y value down here is 0. And then the area is side squared, or like base squared. So the area is really just 5 minus 5/3 x squared. So that means my volume, all I have to do is just add up a bunch of squares. This is not a rotation. This is not pi r squared. So I'm just putting my expression for area here, and then I put dx to make it a volume. And okay, because I'm chopping like this, I'm going from an x, chop, 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 to an x. Starting at x equals 0. Oh, I have to know where this ends. What x do I end at? I need to set this equal to 0. 5 minus 5/3 x equals 0 whenever y is 0. So that means 5 equals 5/3 x multiplied by 3/5, multiplied by 3/5, 3. Okay, so now you know what? We actually have to do this one by hand and integrate it out. So what is this? 5 minus 5/3 x squared. I'm going to have to write this out. in order to like really see what's happening here. So that would be 25 minus 25 over 3x minus 25 over 3x plus 25 over 9x squared. Okay, so 25 minus 25, negative 25 thirds minus 25 thirds is negative 50 thirds x plus 25 over 9x squared. Wow, okay. So that means I have an integral of that. So now I have to do an antiderivative of that. So I'm going to go right to the antiderivative. Okay, so that would be 25x minus 50x squared. It was over 3, but then I'm also over 2, so that's over 6, plus 25x cubed. There was a 9 there, it's over 3, so 27. And now I'm going to going from 0 to 3. All right, so I'm going to plug in here. Luckily, when I plug 0 in, everything is going to 0 out. So this would be 25 times 3 minus 50 over 3 squared over 6 plus 25 3 cubed over 27. Again, it's minus 0. Okay, so this is 75 minus 50 times 3 squared is 9. 9 over 6 reduces to 3 over 2. Okay, let's see. 3 cubed is 27. That cancels. Plus 25, right? Okay, so anyway, 75 plus 25 is 100 minus 50 times 3 is 150 divided by 2. What's 150 divided by 2? 75? Okay, there we go. There's my 25. Okay, last problem. This progress check had quite a few problems on it. Okay, so let R be the region in the first quadrant bounded by this cubic and this line. Okay, so this is y equals 1 minus x cubed. This is y equals 1 minus x, as shown in the figure above. The region R is the base of a solid. Okay, once again, I have squares perpendicular to the x-axis. You should realize by now, at this point in the year, you see squares a lot. Okay, so I have squares coming up out like this of the paper. So what's the volume? Okay, so my base length, first I need a random base. To get this length, I need top minus bottom. So it'd be 1 minus x cubed minus 1 minus x. Okay, and then in order to find area, it would be this squared because I have a square coming up out of the paper. So I'm going to simplify this. 1 minus x cubed minus 1 plus x squared. 1 minus 1 cancels. I'm going to do x minus x cubed. I want the positive thing first, squared. Okay, so then that is the area. So all I'm going to do here is do an integral, and I'm going to add up a bunch of these areas. X minus x cubed squared dx. And because this is all in terms of x, I need to go from an x value to an x value. So my squares start at 0. They end at 1. Okay, so what is x minus x cubed squared? Because this is no calculator problem, you do have to FOIL this out. You can't really do u sub. That'd be x squared minus x to the 4th minus x to the 4th minus 2x to the 4th plus x cubed times x cubed is x to the 6th. Alrighty, I'm going to do an integral of that. So I'm going to go right to the antiderivative here. So that would be x cubed over 3 minus 2x to the 5th over 5 plus x to the 7th over 7 from 0 to 1. And thank God we just have to plug 1 and 0 in because these fractions are pretty wild. So this would be 1/3 minus 2/5 plus 1/7 minus 0. All right, so the common denominator here, I got the common denominator just by multiplying 3 times 5 times 7. 15 times 7 is 105. And then from 3 to 105, you multiply by 35. From 5 to 105, I multiplied by 7 times 3, which is 21, times 2 made that 42. And then from 7 to 105, I multiplied by 3 times 5 is 15. And then 35 minus 42 plus 15 is 8. So 8 over 105. Okay, that was it for progress check part A. I'll make a video for part B. I'll upload that one later on. All right, hopefully that was helpful. See you later.